All right, Bohr's model. Let's finish it up. So at the end of class, we were talking about why would Bohr's model be stable when Rutherford's model was not? And the reason is because Bohr spent a lot of time and energy finding the radii that are allowed, the allowable orbits. And he he said the only orbits that are allowed are the orbits where the circumference of the circle, 2 pi r, would be equal to a whole number of de Broglie wavelengths. Remember, the electron is moving like a wave, and its wavelength would be equal to h over mv. So Bohr spent a lot of time figuring out, okay, the wavelength of the electron, and will that number of wavelengths fit into a particular circumference? Okay, going back to grade 11, when two waves are going through the same medium at the same time, imagine filling your bathtub with water and sitting on the bathroom floor and moving your one finger up and down, you'd create waves. So now move two fingers up and down and you'd create two sets of waves. And when those two sets of waves get to the same point, they interfere with each other. So if one wave was looking like this as it was going through, and the other wave was the exact opposite, they would kind of cancel each other out. And this is called destructive interference. Okay, because one wave is trying to pull the water up like this, the other wave is trying to pull the water down like this. It's at a standstill. The resultant would just be a flat line. But it could be that the two waves are trying to pull in the same direction. So maybe one wave is like this and one wave is like this. And if their crests, the high peaks, and their troughs, the low peaks, are lined up, then the resultant is going to be an even bigger crest and an even bigger trough because they're working together. You would add up the amplitudes of the wave to get the resultant. Okay, so that, and this would be called constructive interference. So then the other thing that we talked about in grade 11 physics was that if you have, and we can do this with a slinky if you want when we come back to class again, but if I have a slinky and I send like a pulse, just a crest, down the slinky, when it hits the other end, it's going to flip over. If someone's hand is holding it, it's going to flip over and come back. So if I send a wave down the slinky, the wave's going to do the same thing. So if I continually move my hand back and forth and send more and more down, then depending on the frequency, I could create interference, right? And so if I can send waves down in such a way that the crests of the one going on its way down perfectly matches the crests of the ones on the way back, what we end up creating is something called a standing wave. And it's called a standing wave because it actually looks like it's standing still in the medium. It doesn't look like it's traveling down the slinky or through the medium at all. It just looks like it's flipping back and forth from a crest to a trough, from a crest to a trough. And I'll show you that because there's those of you that had physics second semester haven't seen this, okay? So what Bohr is saying is, if this is the scenario that happens in a given orbital, if a standing wave can be created, then it'll be stable. And if it can't be created, then it'll be unstable. So he figured out all the allowable orbitals, and that's why he thinks his model should be more stable than Rutherford's, okay? And so an electron orbit will only be stable if it contains a whole number of electron wavelengths. A whole number of electron wavelengths, and this would create a standing wave in the orbital. Okay, and so that means the circumference of the orbital must be equal to a whole number of de Broglie wavelengths for the electron. And so obviously this is dependent upon the radius of the orbital which is why he spent so much time finding the radius of each orbital. Okay? The second piece we need to do is what are the model's limitations. So Bohr's model limitations. Whoops, be good if I could spell limitation. Okay, and there's three really. Okay, the first limitation, and I'm going to say it and you won't understand it till I explain it for a minute or two, but the first limitation is that he could not explain why some of the spectral lines of hydrogen were bright and some were dim. Could not explain why some of hydrogen's spectrum lines were bright and some dim. Now, what do I mean by hydrogen spectrum lines, bright and some dim? If you take gas, take anything, and heat it to the point of incandescence means it's going to glow and give off light, you could then look at that light through a prism and it would separate it into a spectrum, right? Like a rainbow. So think of the prisms that might be hanging in your windows at home, the little crystals. When light hits it the right way, you will get a nice pretty rainbow on the wall across from the prism or on the floor. So any light can be broken into its component colors by putting it through a prism. So what we'll do, and what Bohr and we'll take hydrogen gas, and this will be our next lab. We'll heat it to the point of incandescence. We'll run a current through it until it glows, and then we'll look at the color that it gives off, and we'll see its what's called its spectral lines. And hydrogen has 4 of them. 3 of them are actually quite bright. Hydrogen has 4 of them in the visible spectrum. 3 of them are actually quite bright. 1 is significantly dimmer. Bohr's model could not explain which ones were bright and which ones were dim or why. Okay, so that's his first limitation. We're going to talk about spectra, the absorption and emission spectrum in the next video. His second limitation is that he could not account for very, very closely spaced spectral lines. Could not account. Now, what I mean by account, again, would be could not explain. So could not account for very closely spaced spectral lines. Okay, and so again, heating a gas to the point of incandescence, where it glows and gives off light, looking at that light through a prism, some of the spectral lines are going to be really close together. Sodium is the best example. Sodium has 2 yellow lines that are so close to each other that when you look at the spectrum in class, it's going to be really hard to see them as 2 separate lines. It's going to look like a really big, thick one. Okay, so Bohr's model can't account for why 2 lines would be really close together, whereas in other spectra, they would be far apart. Like for neon, for example, neon has like about 20 red lines, but most of them are not as close as sodium's 2 yellow ones are. So Bohr couldn't explain why they would be close or not close. But his major limitation, the big one, his major limitation is that his model really only works for hydrogen. He could not predict the electron orbits, nor the spectra is plural for spectrum, for elements with many electrons. It really only works for hydrogen. Okay?